Most people hang their plants from a string or a chain, and some of them talk to the plants. You decide instead to hang your plant from a spring with a spring constant of 8 newtons per meter so that it can have fun oscillating up and down. After you hang your plant, you start it bouncing with an amplitude of 12 centimeters, and you see that it oscillates with a frequency of 2 Hertz. After this, follow a long list of questions, A through H. This problem would be too long for a typical exam, but since in this case what we're trying to accomplish here is to learn the topic thoroughly, we've included many parts to this question. Although most textbooks, and hence most instructors, present simple harmonic motion primarily as an energy problem, I've found that students have the most success when they address simple harmonic motion as a kinematics problem. Let's briefly go over the equations involved in describing simple harmonic motion as kinematics. An oscillating motion will be described with either a sine or a cosine function as a function of time. Since our plant is going up and down, I will use y, and having done cosine in a previous problem, I think this time I'm going to do sine. One must be careful, even though we understand that the position oscillates with regard to time, it is inappropriate to present an argument to the sine, cosine, or any other trig function which is not in the units of degrees, radians, grads, or some other angle. For that reason, we require a unit conversion in order to be able to make this expression work. So we recognize that since omega is a unit conversion, it will be some form of 1. We wish to produce radians as our unit inside the sine function. There's actually a stronger reason for this than most students know. The sine and cosine function are in fact only each other's derivative when the argument is in radians. You can't get away with the same thing in degrees. So we'd like the product of omega times t to produce radians, so we need radians in the numerator and seconds in the denominator. If we consider a full cycle of any motion, we recognize that the sine function undergoes a full cycle having executed 2 pi radians. We then need to identify what is the time interval associated with a full cycle. That time interval is the period, which I use the Greek letter tau to represent, and so omega must be equal to 2 pi over the period under all circumstances because it is merely a unit conversion. Recognizing that 1 over period is frequency, we can also write omega as 2 pi frequency. I then like to refer to omega, period, and frequency as synonymous variables. All 3 of them encode how rapidly the oscillator oscillates. A high frequency, a high omega, or a short period all represent something that oscillates quickly. What this means is that given any one of these, you know all 3 immediately through the relationship shown here. Now that we understand the form of our oscillatory motion, y as a function of time, we can very rapidly take 2 derivatives in order to find the velocity and acceleration as a function of time. These equations are given here. We recognize that this is not a complete set of every variable versus any other one in pairwise relationships. None of these variables are versus one another, they're only versus time. So what we need to do is we need to take these expressions and successively eliminate time from the expression so as to get the other relationships that we need to be able to solve any problem that's posed to us at any time. The tricky part in eliminating t is that we see some of these are functions of sine and others are function of cosine. However, we remember the trigonometric relationship that sine squared plus cosine squared is 1, and so we can solve each of these to be either sine or cosine, and then get the simple form we're looking for. As an example, we'll take the position divided by its maximum value. Looking at the expression, this is sine, and so that quantity is in fact sine squared. The velocity divided by its maximum value, a omega, is cosine, and sine squared plus cosine squared is equal to 1. Next, we do the same procedure regarding velocity and acceleration. Velocity over its maximum is cosine, and acceleration over its maximum is sine. Cosine squared plus sine squared is 1. Finally, to get the last pairwise relationship, that between position and acceleration, we recognize that these are both amplitude times sine. The only thing is that the acceleration term has an extra factor of omega squared. Therefore, we recognize that the acceleration is negative omega squared times the position, or we've called that y in this set of equations. It's worth noting the maximum value of each one of these quantities. The maximum value of the position is equal to a, the amplitude. The maximum value of the velocity is the amplitude times omega. And the maximum value of the acceleration is the amplitude times omega squared. Finally, we recognize that in none of these relationships have we referred to why any particular system is oscillating. We've only referred to the fact that it is oscillating. The physics that governs each oscillator is in fact entirely 100% encoded into the value of omega. And we have three conditions that we frequently deal with in an introductory physics course. The first of these three is a mass on a spring. In that case, the omega value is the square root of the spring constant k divided by the mass m. The next instance is a simple pendulum. A simple pendulum is a single point object at the end of a massless string, and it oscillates in accordance with the square root of g divided by the length of the pendulum L. And finally is a physical pendulum, which is some sort of an extended object described not by a mass, but rather that by a moment of inertia for completeness. And the physical pendulum has an omega equal to the square root of its total mass times the acceleration g times the distance d between the center of mass of our physical pendulum and the pivot point, finally divided by the moment of inertia. It's interesting to take a moment and look at each one of these equations. Each one of these equations has a square root. This in fact comes from the relationship between acceleration and position having an omega squared inside of it. And each is the ratio of that constant, which decides how stiff the returning force is, k in the case of a spring, and relationships to g in the case of a pendulum, divided by something associated with how hard it is to bring the thing back to the origin, and that is either mass or moment of inertia. Equipped with these equations, and understanding them in detail, we can solve any simple harmonic motion problem. Now you may look at this and decide, wow, this is an awful lot to remember, but in fact, the reason I derive it every time I talk about it is that all you have to really remember is the first form. The rest can be found by derivatives, a couple of trigonometric tricks, and then you're off to the races to solve anything you need to know in a simple harmonic motion problem. Let's solve those many questions in this problem and see how rapidly we do so through this approach. Before we address the first question, we'll collect a little bit of information from the language of the problem itself. We notice that the spring constant k was given as 8 newtons per meter. That's an MKS unit. The amplitude was given in centimeters. We'll convert that to meters to make it an MKS unit. And finally, we were given a frequency of 2 Hertz. What we recognize about frequency is this is one of the triplet of synonymous variables, and so by the time we're ready to solve this problem, we'll really be dealing with the frequency not as a frequency in Hertz, but rather as an omega in radians per second. Let's look at part A. What's the period of our plant? Well, the period is one of that triplet of synonymous variables, and the period is related to the frequency by being 1 over the frequency. So 1 over 2 Hertz is 0.5 seconds. Part B poses the question, what is omega? Well, this is really getting to the heart of the matter. Omega is either 2 pi divided by the period or 2 pi times the frequency. Since we were given the frequency, we'll use that so as to avoid any mathematical error we might have made in part A. So 2 pi times the frequency is going to be 4 times pi, which is equal to 12.57 rad per second. In part C, We're to determine the maximum velocity of the plant. What we remember is that the maximum velocity was equal to amplitude times omega. This is because one factor of omega came out during the process of taking the derivative. Since we know both the amplitude and the omega, we can multiply these to find that the maximum velocity is 1.51 meter per second. Next, we're asked for the maximum value of the acceleration. This is also easy. We remember that in the process of determining the acceleration formula, we took two derivatives, bringing out the factor of omega twice. So the maximum acceleration is amplitude times omega squared. And since we know both of those terms, we get 18.95 meter per second squared. Part E asks us to determine the velocity of the plant when its displacement from equilibrium is 4 centimeters. Let's make this into a well-formed question. What we'll need to do in order to satisfy the question is supply a value for the velocity variable. This is an ill-formed question because the velocity variable, in fact, accelerates back and forth between plus and minus its maximum value. To make this question more specific, we need to find the velocity under the condition that the position is equal to 4 centimeters, which in MKS units is 0.04 meters. We recognize that the relationship between position and velocity is found by taking position over its maximum, squaring it, adding that to velocity over its maximum, squared again, and it really doesn't matter whether we assign the position to be sine, cosine, or in fact something in between with a phase angle. Cosine squared plus sine squared will always be equal to 1. Using a value of 0.04 for y, this expression will have 1 and only one unknown. Solving the above for velocity, we get that v is equal to 1.42 meter per second. Part F asks us to find the acceleration of the plant when its velocity is half of its maximum. We'll formulate this as a well-formed question, and we recognize that to satisfy the question we must supply a value for the acceleration variable, which is not a constant but oscillates between plus and minus of its maximum value. To make this into a well-formed expression, we need to supply the condition that velocity is velocity maximum over 2. To solve this question, we need to find the relationship between the velocity and the acceleration, and we recognize again this follows the trigonometric identity that the velocity over its maximum squared plus the acceleration over its maximum squared will be equal to 1. Since we're asked to find the moment when the v is equal to half of its maximum, the first term is simply 1/2 quantity squared, and the acceleration turns out to be 16.41 meter per second squared, less than the maximum of 18.95, as it must be. In Part G, we've been asked what amplitude of oscillation would produce a maximum acceleration of 9.8 meters per second squared. That's the same acceleration as gravity, and we recognize that the maximum acceleration is given by the formula amplitude times omega squared. Therefore, if we desire to get a maximum acceleration of 9.8, we can solve for the amplitude using our previously known value of omega. This yields the result that the amplitude should be 0.062 meters, or 6.2 centimeters. Now let's think about this for a moment. When your acceleration is equal to g, this is the moment when you feel weightless. Our plant in the previous problem actually exceeded the acceleration of g by nearly a factor of 2. If this plant was a hanging vine, then in fact it was flapping that vine up and down like wings at the moment when the acceleration exceeded 9.8 meters per second squared. Kind of a funny sight, and you probably wouldn't actually do that to your plants. Lastly, we're asked to find how far the spring is stretched when the plant is at equilibrium. and we recognize that equilibrium is a force problem. The first step in every force problem is to draw a free body diagram. This is your plant, and the plant is receiving a gravity force, m times g, and will be receiving an upward force due to the spring of k, the spring constant, times the stretch of the spring, which we'll call the y of equilibrium. This is a one-dimensional free body diagram, and if we are truly in equilibrium, there won't be any acceleration at the moment we're looking at, so either direction could be plus. In this case, we will say that the spring constant times the y at equilibrium will be equal to mass times gravity. The spring constant we know. It's 8 newtons per meter. However, what's the mass? To solve this question, we remember that the spring constant and mass are related to the omega in the motion itself, so that omega is the square root of the spring constant divided by the mass. Therefore, we first solve the problem to determine the mass of the object given the information at hand, and then, once we know the mass, we'll be able to plug it in and find the equilibrium y, or the amount by which the spring is stretched from its natural length when the plant is hung but not oscillating up and down. Solving this relationship for m, we find that we get a mass of 0.0507 kilograms, and placing this mass into the previous relationship, we'll be able to solve for the y at equilibrium, which yields the result 0.062 meters. Exactly the same as the amplitude of the oscillation that leads to a maximum acceleration of gravity. Think about that. The reason is that if the stretch of the spring at equilibrium equals the amplitude, the top of the motion has the spring being at its rest length, giving gravity as the only force, and therefore the acceleration at that moment is 9.8 meters per second squared. Kind of makes sense.